we're going to talk about a more complicated question here now. So situation, pause the video and just have a quick read. Should look like this. Make sure that you're able to, let's just quickly plug this one in. Make sure that you're able to go from the text to the diagram, because sometimes the diagram is not there and you have to draw it yourself. So this time we have a scale pan. Scale pan's a bit like a lift. Okay, it's a bit like a lift, and inside it, it's got so the scale pan, which is the triangle. Inside has got these forces here, and they've got some masses, 0.4 and 0.6, because you have to change them to kilograms. And the whole thing's also accelerating with A. So find the tension in the string. What we're going to say for these kind of questions is the best way to handle it is to look at the system as a whole first. So, you know, think about that particle there. That's the whole system. So what forces are acting on it? Well, there's some sort of tension from a string up here, and then there is the weight holding it down. Remember, we're thinking about the whole system, okay? I'm not sort of getting intricate and thinking about reactions between the blocks and stuff. No. I'm considering it as one whole system. So 0.4 G would be down, and 0.6 G together is G down. So the resultant force, T minus G, is what you're going to get when you put this into F equals at MA. So T minus, this is minus G altogether, is equal to M. M is the mass, 1 kilogram, and the acceleration's been given to us. And we find tension. So that's what we want to start by doing. Okay, that part's not so bad. So tension in the string, a bit like connected particles we've said so far, you can consider it like as one system as a whole. TL Maths have got a very good video about turning these kind of situations into force diagrams, which you might want to have a look at as well. Okay, so find the force exerted by, so exerted like done to B by A. Right. Here's the shortcut for these questions. Start with the topmost block and work your way down is the way to go here. Okay, there's a lot of reasons why, and I'll sort of reveal these here at the side of the screen. They've got things to do with Newton's law, like an equal and opposite reaction, and so on. But at this stage, you probably just want to be able to get into the question. So we start with the top block and we work our way down for these kind of questions. And I'm only looking at this block itself. So I'm looking at the block A. So block A, what forces are acting on A directly? Well, it's got its weight down, which should be 0.4 G, and it's sitting on some sort of surface. So there's some reaction from B as well. Okay, there's that reaction from B. So resultant force, we've got resultant force. It's not as easy as just saying that they're balanced, I'm afraid. Okay, in fact, they won't be balanced because the whole thing's accelerating. If you remember, when forces are unbalanced, things accelerate, and this is accelerating, so they're not the same. R is not 0.4 G. Instead, you need to think of this as the resultant force overall, and then set it equal to MA. So R minus 0.4 G equals MA. It's the mass for the block. Remember, this is all about A, okay? I'm looking directly at the things acting on A. And the acceleration is the same throughout the question. That's what we said. If you do this, you will get 4.1 newtons. And you might think, well, you haven't answered the question. And you're right in a sense. I have found out, by doing this, I found out the reaction that A faces. In other words, I have found out what B is doing to A. That's what I found out. And the question says, well, what's A doing to B? They will be the same. Okay, they will be the same because the blocks are remaining in contact with each other. They're not sort of like accelerating away at different rates and so on. Okay, when they stay in contact with each other, what A is doing to B is the same as what B is doing to A. Okay, there's quite a bit of theory behind that, and you can pause the video and have a look here. But it's sort of a trick for how we answer these questions. Now, we've sort of dealt with this block here and we found out some forces. What's the force done to the B by the scale pan? Well, we're going to do the same sort of thing again. Let's actually consider the next block. So that's what we said, we work our way down. So let's consider B as a particle. So what is acting on B? Let's start with the easier part. So its weight is pulling it down, okay? Is anything else being done to B? Well, A is sitting on top of it. And it's sort of like pushing down on it because it's sat on top of it. In fact, we found out exerted on mass B by A. Well, we want to use that one there. So there's also 4.1 down. So it has its own weight, and it also has A pressing down on it. So it has two forces there. Well, how is the thing not falling through the floor then? Well, that's because the scale pan, the lift, in other words, I'm going to call it like R2. So that there's some reaction force there that's keeping that one up. So same again, you're going to find your resultant force from this one here and set it equal to MA. And that's 4B. So you will be using the mass of B. Acceleration, the same again. Drawn a little bit differently here, I would draw it like this. So the driving force, the leading force is R2, or they've called it S here, and 4.1 presses down, so that acts the other way. The weight pushes down, acts the other way. That's the mass of block B, that's the acceleration, and we get our answer. Okay, so it's 10.3. 10.3 apparently for this one as well. So there you go. The solution to these kind of questions is working your way down. So you do block A and then block B. And when things stay in contact with each other, it means whatever the top one does to the bottom one is doing to the top. But that idea sort of just goes alongside drawing out the particles separately, and you draw the forces that act directly on the particle you are looking at. That's the way that you must draw your force diagrams.